Cool. Okay, we're going to talk about concavity in the second derivative test. So first, let's talk about concavity. Now, let's start off with something simple. Let's start off with a line, and let's build on what we already know. Let's draw a nice line here. Okay, so if this is my line, we know that slope, that the first derivative is slope, right? Slope of the line is the first derivative. But beyond that, think of what slope really means. Slope is just the rate of change of y. It's the rate of change of the function. It's telling me if, for example, in this case, it looks like I've drawn something with a slope. We pick two convenient spots, like there and there.
Approximately one. Nope.
It looks like I've picked a line with a slope of 3/4. All right, rise over run, 3/4. Now, what's that saying? That's saying that the rate of change of y with respect to x is 3/4, right? That y is changing only 3/4 as fast as x is. What if they were changing at the same rate? Then what kind of slope would we have? 1. Be a 45-degree angle, right? But in this case, the rate of change of y is a little bit less than 1, so we get a shallower slope. Okay? It's most convenient for us to think about that as slope because that's a parameter we can attach to lines. But if we're talking about a curve, something that's not straight, oh, we don't want to do that. I just want to do this. There. And not that.
Well, can you just erase like a certain color?
Okay, just do that. Yeah. Okay. I don't know. There's probably some. I don't know. I bet you can't actually. So let's say I've got here's F. There's F. Now this time, if I pick a specific spot on here, let's pick this point right there. Okay.
Oh yeah.
Yes.
Yeah, that's a question.
Yes.
So, like in the derivative, the x is the same as the x. Original.
What do you? Here, let me get a new sheet here. What do you mean? What do you mean?
It's like the line of the derivative has the same like x value. Like so, like one corresponds to one y. It's like y.
Oh, if you mean if it were a line with a slope of 1.
You know what I'm saying? Like if you would have like a line and you take the derivative of it.
Mm-hmm.
Like so.
Oh, okay. Yeah, the slope's the same everywhere. Is that what you're getting at?
No, I'm saying like for
No.
for the values of the derivative, that y is the slope of the original equation and x is just the x derivative.
Y prime
Right, y prime
is the slope. Right, exactly. Y prime is the slope of the original function at that value of x. See, like that's what we're getting at here. So, for example, here, if this is my point of symmetry, or my point of tangency, this is the x value that we're plugging in, then at that value of x, we have that tangent line, right? It's got a certain slope, right? In other words, at this moment in time, if we measured the slope of this thing, which, we could do, if we just, let's just extend that out a little bit. Then, if we want to calculate the slope, looks like it crosses, I don't know, that's good enough right there. And where's another spot where it crosses? Right about there. So that's a pretty good estimate of the slope. It looks like we're running by 1, 2, 3, 4, 5, 6, 7, and we're rising by 4. So the rate of change of y, of the function, with respect to x at that point is 4/7, right? That's giving us a number that tells us the rate. That means a slope for us. The slope is relatively shallow. If we go back here, we'll see one that's even less, but if we go up here, we'll see a rate that's bigger, right? If I were to pick a point of tangency up here, I'm going to get a tangent line that's steeper, right? Does that make sense? Okay, so we've already talked about all that stuff, but now what we want to talk about, when we talk about concavity, we're going to get into the next level up. Now, instead of talking about the rate at which the function is changing, we want to talk about the rate at which the slope is changing. So we're taking the rate of change of the rate of change of the function. In other words, the rate of change of slope. Now, we've already got this idea conceptually. If the ant moves from point A
To point B.
to point B, which is right here, let's say, and here's the tangent to point B, it looks kind of like that. What's happening to the slope as he moves from A to B? It's getting steeper. So wouldn't you say then that if the number associated with the slope is getting bigger, the rate of change of the slope is positive because it's increasing? So if we attached a number, we said that at this point right here, the slope of the tangent line, or let's use it as a derivative. We don't want to write it as let's write it like this. At this point right here, y prime was equal to 4/7, but let's say right here it's about 1. Okay, at this point, so it's gone from 4/7 up to 1. Right? The slope is increasing, so the rate of change of slope is increasing. Now, what would a rate of change of slope look like? A rate of change is a derivative, right? So we're doing this. We're taking the derivative with respect to x of y prime. Well, isn't that just y double prime? Yeah. Right? So the second derivative is really charting that. The second derivative is telling us the rate of change of the first derivative, which we know to be slope, at least graphically, right? Now let's take a different example. On the same curve, on the same grid, let's take this guy. What if we've got one this is G, and G is doing that?
Decreasing?
Okay. Yeah, look at, if we take, say those same spots, here's x equals a, and we've got a slope like that, and then here is x equals b. Well, those are bad points.
Yeah, they are.
We'll pick different points.
We're picking
We're picking a point right here. There's point A for us, our new point A. There's the slope, and here's point B. X equals b. Now what's happened there? We've gone from something like roughly 1/4, let's just say it's about 1/4, to something like, oh, I don't know, negative 2/3, something like that. So we've gone from a positive number to a larger negative number. It's definitely decreased. So we'd say the rate of change of the first derivative is negative there, right? So then doesn't that stand to reason that up here in this first one, at this point right here, now let's just focus. Here's where we're focusing, right there. We focus at that point because when we moved to the right, our slope increased, right? And if we moved from down here, our slope would have increased to get to that point, right? This is a place where we can say that y double prime is positive. The rate of change of the slope is positive. It's increasing, right? And a positive rate of change means an increase. Down here, if we take a point in here, right, let's just focus on that point, where the slope is in the process of going from positive to increasingly negative, here's a place where we could say y double prime is negative. Second derivative is negative. The rate of change of the derivative, the rate of change of the slope is negative because it's decreasing. Can you make a general observation about this? Can you correlate this with the basic look of the curve? What do you suppose has to be true about the nature of a curve where its second derivative is positive compared to where it's negative? True. What do you notice about the shapes of those curves there?
If it's negative, it goes down.
What do you mean goes down?
That's decrease.
Oh, okay, now we're on something. Say that again, Billy.
Your maximum.
Well, okay, it doesn't have to be a maximum or a minimum, but it's a place. Let me refine that just a little bit. If it were a maximum, that would have to be a place where the second derivative were positive, right? Doesn't that make sense? If it were a maximum, it would have to be a place draw a maximum. So here's a maximum. That would have to be a place where the rate of change of the derivative were negative, right? At least if it were a smooth, rounded maximum. Does that make sense? Because that's the only way that could be. The slope has to be going from positive to negative. We said that, right? That's the nature of a smooth peak, is it's going from positive to negative. That's decreasing by nature, decreasing slope, right? So at that point right there, we know second derivative is positive. What about a minimum? That's got to be the opposite, yeah, right? Because at a minimum, we're going from a negative slope to a positive slope. So that's got to be an increasing second derivative. Okay? Now, they don't have to be maxima or minima, though, to talk about second derivative and how it relates to the shape. If we go back over here, we don't see any maxima or maximum on this blue curve, right? But there's still something about its shape that's reminiscent of that example we just looked at. What do you notice about the shape of a function that has a second derivative that's positive? Let me ask you this. If an ant walking along this curve were to look forward, say that the ant is actually walking on top of the curve. If the first derivative, the rate of change of the first derivative is positive, could he see the terrain in front of him? So in other words, if the ant is standing right here, stands up on his tiny little hind legs and looks forward, can he see the terrain in front of him?
Yes, he can.
Okay, what about if the second derivative is negative? He stands up down here. Can he see the terrain in front of him there?
No, we cannot.
No, it recedes in front of him. Right?
Oh, I see.
So the word we give that, and we don't actually define it in terms of ants, but the word that we use to describe that kind of a look is either concave up or concave down. If the tangent line, if you can do this, if you draw, another way to think about this is, at the point where the ant is standing, if I draw a tangent line, if the curve is completely above that tangent line, then it's concave up, isn't it? It's warped upward. One way to describe it is it catches water. If it's raining on the function, it's going to tend to catch water if it's concave. Now, here's the ant standing down here. If I draw the tangent to the curve and the curve is completely below the tangent line, locally speaking, then it's concave down. It's going to tend to shed water. Okay? So we can associate concavity with second derivative. Positive second derivative means upward concavity. Negative second derivative means downward concavity. The larger the second derivative, the more concave it is, the more curved it is. Yes, sir?
I have a really stupid question. Okay, so if that was flipped and it was like mirrored across the y-axis, it would still be concave up and concave down?
Yes, yeah. If it were right, if it were mirrored in the y-axis, it would still be concave upward. If it were mirrored in the x-axis, it would be concave downward. Yeah. Okay, so there's one. Yes, sir.
Wait, so if it was mirrored about the y-axis, then it would be from up to down.
Mirrored about the y-axis, then it would just look like this. Then it would look like that, right? That's still concave up, though, right? Because see, it's still bowl shaped up. If I draw a tangent line under this, the curve sits on top of the tangent line, not below it.
Which calculus that slowing up?
Right. There it is.
How's that calculus ain't going to see in front of him, though, if the slope is that way?
This way.
Say it again.
If he's staying there, isn't he not going to see
Yeah,
it?
but it catches water.
No, he's gonna. If he's standing here, he's gonna see in front of him. He can see the slope up in front of him.
Okay.
Right, he's walking down the hill, but he can see the thing leveling out.
Okay.
Right. Okay. Now, so let's take a. Does somebody want to come up here and try to maybe tell me? See if you can define the places where this function. I'll draw it in black. I want you to maybe in red outline the places where it's concave up, and in blue outline the places where it's concave down. Anybody want to try that? Wait, Brave, come on up.
Is it left or right?
Don't ask Siri. She won't
Okay, so
know.
in red I do where it's concave up.
Yeah, red, let's do concave up, blue, concave down. So what's that going to be?
Concave up.
You sure?
Oh.
No.
Okay, so what I'm looking for here is, I'm not looking for the tangent lines. I want you to pick, would you agree that this curve
Circle the
is,
areas.
Just go back.
that this curve is transitioning from concave up to concave
Yeah.
down in certain places? So you're starting, okay, so red will be concave down. Start over
Starting
here, that's
down.
concave down. I want you to stop with the red, just trace along the curve. Stop with the red when you think you get to a place, and it's kind of, you're just eyeballing it,
Keep going, keep
to a
going, keep
place
going.
where it's going to switch.
Keep going. Stop.
Oh yeah, probably about there.
Blue. Yeah.
Okay, now we got to go blue, don't we?
Blue.
Because from that point, now all of a sudden it starts to be bowl-shaped up. You got it, I think.
Keep going, keep going.
Okay, good, good.
Go, 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 go.
No, let me do this. Let me do
Stop!
this.
Oh, he's just going to overlap it. I see.
Go, go, go. To the end.
Shucks, I can't see what I'm doing. And like right there.
Okay.
Yeah, why'd you change
No.
it?
Okay, I think that's good there, but I think that's, you got that one right, but I think you missed one back here a little bit. I think back here, shouldn't that red go back to about,
Yeah.
so you got to flip to red. It's easier to do when you're not doing it. I can.
There you go. Nope, keep going. A little bit.
Okay, that's about right. Good. So we got these places of transition, right? We could divide this thing up. If we put in some vertical lines to divide this up, like so, right about there is going to be. Well, that's not one. I think I need to calibrate this thing a little bit. There's one. Let's see. There's one, and there's one, right? And so we've got second derivative negative, second derivative negative, second derivative positive, second derivative positive. Well, what's happening at the transition places?
0.
Yeah. In this case, those are places where the second derivative is equal to 0. Okay, so there, and there, and there.
Red, not green.
But it wouldn't necessarily have to be. It could also be undefined. Because this is what you, now we call these places, by the way, these are called inflection points.
How do you determine whether it's undefined or 0?
Just the way
Yeah.
inflection points are where they transfer from concave up
Yeah.
to concave.
Yeah. Inflection points are places where the sign of the concavity changes, sign of the second derivative changes.
How do you know whether it's 0 or undefined?
If it's a smooth transition, it's generally 0. And if well, these are all pretty smooth. I think these would all be 0. It's a little harder to see with, it's not so obvious with second derivative as it is with first derivative, because first derivative is a slope and it's easy to visualize. But if there's a place where you can kind of imagine what it would look like, because it would be a sudden transition of the slope. Here the slope is changing in a nice smooth way, but if the slope were all of a sudden to go from
Similar to the cusp?
kind of like it's where the first derivative would have a cusp. The graph of the first derivative. Okay, now the inflection points are the places where we transition from positive to negative or negative to positive, right? How do we find those? Now this is the thing I want you to get here. When we're looking for inflection points, the relationship between inflection points and the second derivative is identical to the relationship between extrema and the first derivative. That's really cool that we can do that in calculus. We've taken the concept that we talked about with the first derivative, and we've just moved it up one level of differentiation. We have to go up to a second level of differentiation. All the relationships stay the same, but we just changed the names. Instead of first derivative, it's second derivative. Instead of extrema, they're inflection points. And they manifest themselves differently on the graph, sure. These aren't, we know that extrema are either peaks or valleys. Inflection points look a little different, right? But we look for them in the very same way. If I want to find all the inflection points, we know that inflection points are a second derivative issue, just like extrema are a first derivative issue. Now, how do you suppose we hunt for inflection points with the second derivative?
You find the critical numbers of the first.
We find the critical numbers of the second derivative, and what do we do with those critical numbers?
Plug them in and test them.
We test them. We test them just like we did with the critical numbers of the first derivative. We test them to see if they are sign changes, if they represent sign changes of the second derivative. If they do, they're inflection points. If they don't, they're not. Okay, the best way to do this is just look at some examples. This is really fun stuff. This you're gonna like this. This is good. Because what this tells us, we get about 4 birds with 1 stone on this one, which is pretty good. Doesn't matter where you are, I mean, killing 4 birds with 1 stone is a pretty good deal.
I watched my cousin kill a bird with a stone once. It was really funny.
Yeah.
It's really funny.
Okay, so yeah,
It was an owl.
yeah, yeah. Okay, so so not only are we going to be able to figure out where concavity changes, Nolan stumbled onto something else really important here, and that is we can use the second derivative as a tool for finding out what's going on at first derivative critical numbers. Okay, let's take an example. Let's take something like, what's a good one? We'll pick something not too wacky for the first time. This guy. Let's analyze
I'm going to erase my top scores.
Okay, let's analyze this function. Now this time, what we're going to do is we're going to use not only the first derivative, but the second derivative. And as a general tendency, you want to work as far down our table as you can. So you'd rather work on the second derivative line than the first derivative line. It's much more economical to do that. You can do less work. Certain functions are going to be amenable to calculating a second derivative and certain aren't. Polynomials are easy, right? We'd rather differentiate them more times because the result ends up being easier, right? So when we start with a polynomial like this, now what's the first derivative? Okay, not bad. We can deal with that. But if we scoot on down to, I'll leave a little space for doing work with the first derivative, but if we scoot on down to the second derivative, that's really simple. What's that? Okay, let's find critical numbers for the first and second derivative, and then we'll build our table. Now, for the first derivative, if we set, there's no place where it's undefined, right? First derivative is a polynomial. There's no danger of dividing by 0 or taking even roots of negative numbers or any of that nonsense. But we do want to know where it equals 0. So we could factor this, right? What could I factor out? No.
4x squared.
Good. 4x squared, leaving me with okay. And so if I set that equal to 0, then finding the zeros is pretty simple. I get zeros at either x equals 3 or x equals 0. Good. Okay, and so if we start our table down here, okay, so we know that we've got 2 critical numbers here. We've got critical numbers at x equals 0 and at x equals 3. Those are places where the first derivative was equal to 0, right? Okay, so those are potential whats? Well, they are critical numbers. They're potential, well, I mean, maybe that too, but first derivative we're mostly concerned with, yeah, extrema. Those are potential extrema, right? Could be maxima or minima, right? Or both. So, what about the second derivative? Let's go ahead and factor the second derivative. Let's find the zeros of that and see what's going on there. Leaving Okay, once again, if we're looking for second derivative critical numbers, and maybe I should, these are regular critical numbers up here, aren't they? What about our second derivative critical numbers? No place where it's undefined. What about where it equals 0? 2?
0.
Or x equals 0. Okay, so what's going on there? Then we get a double critical number. X equals 0 is a critical number of both the first and the second derivative. At 2, we get a second derivative critical number. Okay. So now what? If we want to figure out what's going on here, if we want to find the extrema, what's one way? What's the way we talked about last week for determining what is going on with that critical number right there? We could test points where?
Second derivative.
Well, we had talked about that last week. If we ignore this last row, if I want to figure out what's going on here, I could do the first derivative test, and I could pick test values between x equals 0 and 3 and bigger than 3. And by knowing what's going on with the first derivative, if there's a sign change, I know that I've got an extremum there, right? But here's where Nolan stumbled on something pretty good. What if we take the sign of the second derivative at x equals 3? Okay, now let's do that. If I want to evaluate f double prime of 3, what's the sign going to be? I'm going to get, what sign is that term?
Positive.
Positive. What sign is that term?
Positive.
Positive. So I'm going to get back a positive result. And so a positive second derivative means what kind of concavity? Upward. Here's how you can remember it. A positive second derivative, positive means happy. Your function is happy to be positive. And so you know that this is then what?
Positive.
Well, I mean, what kind of right? But I mean, what do we call that? If it's a 0 of the first derivative with positive concavity, it must be a minimum, right?
That's what it is.
Right? Because look, if I've got a 0 of the first derivative, that means that it's got a horizontal tangent line, right? If it's got a horizontal tangent line and positive concavity, if the whole function sits on top of the tangent line, then that means it's a minimum, right?
Oh my goodness.
Right? Isn't that cool? Isn't that cool? So we know then by the second derivative test.
Okay.
You see how that works?
You're asking too much.
So we know that a 0 first derivative coupled with a positive second derivative automatically means minimum. With relatively little effort, we can determine that. That second derivative test, when it works great.
So is the other one negative?
Okay, but now what about the other one? The other one's indeterminate. The other one, at the other first derivative 0, there is no sign of the second derivative. It's 0, right? And so what do we do then? There's two possible things going on here. We know that we have a horizontal tangent line, right? And we know that our second derivative has a value of 0. There's only two possible scenarios there, one or the other. Either it's a what? What's one thing it could be? Say it again. A what? Well, I mean, it's the tangent's horizontal. So one thing that could happen as a horizontal tangent is it could be a minimum or a maximum, right? It could be an extremum.
Yep.
The other thing that could be happening here is it could be an inflection point.
Yes.
And we actually looked at some of those even last week. Remember I drew one of these for you? Where we had a function that did this. Right? And we said that this one has a horizontal tangent line. So that's going to be a critical number, isn't it? We're going to get a 0 of the first derivative, but it failed to be an extremum. Right? So that's the other possibility, is it could be an inflection point. So which one is it? Now the easiest place to work is, and this is my own kind of philosophy of this, but trust me, this works. You always want to work as far down in the table as you can. So let's go ahead and pick a test point between 0 and 2. Okay? Let's pick a test point like, for example, 1. And let's figure out the sign of the second derivative there. Okay? what's the sign of the second derivative? If one
Negative.
is going to give us a positive factor times a negative factor, which makes it negative. Aha. Okay. So then what does that tell us that this 0 of the second derivative is here? If it's a place where we're changing
It's an
from...
inflection point.
Yeah, that's an inflection point. Okay, everybody see that? Okay. So here we have an inflection point. Okay, now in order to find this one, what do? I've got to pick a point down below somewhere. So let's pick a point like -10 or -2 or whatever. It doesn't matter. Might as well pick one that's extreme so it's easy to find the sign. If I pick -10, what's that sign going to be?
Negative.
What's that one going to be?
Negative.
Negative times negative? Positive.
Negative.
So this one is also an inflection point. And if we wanted to graph this thing, we can do that, right? We can just from that, if I even just know what the y value is of this one point, that gives us a pretty good idea of what the sketch of this thing must look like. When x equals 3, if we go back to our original function, what is y? I'm going to get, 81 minus, not 81, yeah. I get 81 minus 108. So 81. So what is that? -27.
Sure.
Right. Okay. So there's the ordered pair, right? And so if I wanted to graph this guy, we could just sketch a little graph of this. If that's the x-axis. And there's 0, so there's the y. Whoops. What was that?
You just pulled that up to the bottom.
I don't want to do that. Get down there.
What's that?
I don't know. Yeah.
Which?
And there's the y-axis at 3, -27. So let's just say that's... What are you doing? At 3, -27, so let's just say that's right there. Okay, there's the point. 3, -27. I'm going to have a minimum, right? At x equals 2, I've got an inflection point, and then again at x equals 0, I've got an inflection point. So if I had to draw that, doesn't it have to kind of look something like this? I'm going to be concave up, concave down, whoops. Concave up, concave down, concave up, something like that.
Yeah.
Does that make sense?
So is it gonna? Oh, okay.
But can I have any other extreme in there? Oops, hang on a second. So I messed this up, didn't I? How come that's wrong? It has to be wrong. What I drew. How come?
The scale's pretty off.
What's there? What's there?
Maximum.
Can there be another maximum?
No.
No, can't be. There's only one of the two first derivative critical numbers panned out, so there can only be one extremum, and there it is. So I got to redraw that. We got to probably do something like this instead. It's going to go up, and then it's going to change, and then it's going to go like that.
What? Oh, okay.
See what I'm saying?
No, I got lost there.
So I've got an inflection point there and an inflection point there. It's concave up, concave down, concave up.
Oh, I see.
You see? And that's pretty accurate. The scale's going to be off a little bit, but that's basically what it looks like. Isn't that cool? I think that's so cool.
These knees.
It is bee's knees.
What would you use it for in real life?
In real life, you would use it for optimization, first of all. So we're going to do, when we get up to section 3.7, 3.7 and 3.10 are just, they're sections with nothing but story problems about optimization. Things like,
A lot of story problems.
so it'll be stuff like this. Say you've got 100,000 feet of fencing, and you want to fence in a pasture that borders a river. You only need fence on 3 sides. How would you organize that to maximize the amount of area enclosed?
Why would you not fence off the river?
Well, now you would, of course. Pretend, no, that's a bad example.
Yeah, it is.
That's an environment. That's not a very great example. It borders a sheer let's say a rocky cliff, so they can't.
More reason.
Like the gorge.
No, they can't. It's like so they're running into it. It's high.
Oh, okay.
They're at the
that's
bottom
right,
of the
it's
cliff.
rough, so I was like, this is-
And so, but it's so steep. It's so steep that none of those predators could possibly get down. So all we have to do there is just fence three sides. But how do you do this in a way where you're going to get the most enclosed pasture for your fixed amount of fencing? That's an optimization problem. It's not a square.
Sounds like you can
It's a
master in
square,
that.
but it's not a square.
Can you master an optimization?
Yes, if you master in math, you master in optimization. So that's how. And then if you want to look at things that are even a little bit more precise than that, like let's say you want to find the point of what we call in economics the point of diminishing returns. You want to find the point where you're still increasing your profits, but you're increasing your profits at a decreasing rate. That's when you got to start to shift gears. And so you got to be able to identify these key markers or you're going to go out of business. So
That one I can understand.
so that's where you use it. Okay? When do we get out of here?
I don't know, but Samuel Lindsay's missing a big day.
55?
55. We've been in here for over half a year. Boy, you should know this.
Yeah, I come on. You know me better than that by now. I'll never know that stuff.
You're not knowing something? Maybe I don't know you very well.
Okay, how about this? One last example. This is a really good one, too. I don't think we'll have time, maybe, but I'm going to try. It's a quick one. Here's our function.
Samuel Lindsay's missing a big day. Are you recording this?
Yeah.
Yeah.
F prime of x. What's f prime of x here? If f of x is x to the fourth.
4x to the third.
Okay, 4x cubed. What's f double prime?
12x squared.
Okay, so if we made our little table on this thing, we could. Where are the critical numbers of both f prime and f double prime? The first derivative and second derivative critical numbers are both where? I mean, if I set those equal to 0. They're both at x equals 0. Sure. So if we make our table,
Is there...
so the critical number we get at x equals 0, the first derivative is 0 and the second derivative is 0. So it's indeterminate. In other words, the second derivative test failed here. Right? Just like it did in one of the examples on the first one. If we had gotten a sign there, we would have known that the function was either happy or sad. And we would have known from the concavity what kind of a first derivative critical number that was. But a second derivative critical number coinciding with the first derivative critical number doesn't help us in that respect, right? So we got to test some points. Now, where do we test the points? Theoretically, you can test them anywhere, but you're better off going further down.
100
So 100 and negative 100 is the suggestion. Either way, being as the second derivative is an even function, what is its value always going to be?
Even.
Well, positive, right? If I put in positive or negative values of x, I'm always getting back a positive result in this case. Right? X squared is always positive. So if I get back 2 positive results, then is this a point of inflection? No, because a point of inflection would be a transition of concavity. This is going from concave up to concave up, right? And so what it is. So what that means now, you got to think about, you got to really focus on this a little bit. If this one point at x equals 0, how could a single point have its own concavity? It can't, can it? Concavity is by definition, that's a relative term. It can only be defined relative to the values of x next to it, right? Doesn't that make sense? Because if it's going to be bowl-shaped up, you can't have a single point in space that is bowl-shaped, right? I mean, it's just, it's a point. If the points around it behave in the right way, then the curve is bowl-shaped up, right? And so this one little isolated place where the second derivative equals 0 is meaningless because every place around it is positive, right? And so here's what you do with this. This is, once again, this is the part, this is going to be my contribution to calculus mankind when I write this, because this is, these rules are, seriously, this stuff is good. If right here, where you've got this acts like a continuous positive, and all you do is you just put a plus sign next to the 0. because the concavity, it's not a transition. If it's an isolated place where the concavity is 0, that has no meaning. That has no meaning. If every point to the right of that, or for you guys, every point to the left, and think about this, if every point to the left is concave up, and every point to the right is concave up, isn't that one also concave up at that point?
Mm-hmm.
Think what this looks like. If we graph the function, so it looks like this. That's what the function we're talking about looks like. At that point right there, isn't that part of an upward concavity? Right? Okay. So then, the other way we can think about it is, if this is not a point of inflection, it must be a relative extremum. Right? And so, it's which kind of relative extremum could it be? If it's concave up over here and concave up over there, it has to be a minimum. Right? Make sense?
It's like a grapefruit in a bowl.
Okay. Yeah.
With his female side.
Yeah, it's very artistic.
How do you know that in between 0 and 100 there wasn't like a something like that?
In between, because there were no critical numbers. There would have had to have been another critical number of some kind. Remember, the only critical numbers is where all the interesting stuff happens. The absence of critical numbers means boring, monotonic.
I feel like we got a lot accomplished today.
Oh, we did. That was a good day.
That last problem.